3.2, solving quadratic equations by graphing. This is fairly easy. This isn't bad. All right, this should be okay. As long as you know how to use your calculator. All right, that's the big thing. After that, like, it's all calculator work. Like, there's really not a whole lot of handwork to go with. So, Miss Keen, hang tight to it for now. All right, everybody good? Here we go. A couple of definitions. Now, the quadratic equation, that's basically just a quadratic function that's set equal to a number. So it's nothing that you haven't seen before. It's just that you have, instead of function notation, like you do right here on this part of the slide, see how it's f of x equals x squared minus x minus 6. Down here it'll be x squared minus x minus 6 equals 0. Alright, so that's the only difference. There's no function notation to it. The standard form, that's old stuff. Okay, they put it in here twice to make sure you know it. So ax squared plus bx plus c. Remember that. Make sure we know how that. Okay. Now, the next two definitions, roots and zeros. Essentially, here's the deal. Okay, this is probably like one of the most confusing parts to this chapter. So I'm going to try to make it not confusing. That's my job, right? Here is a function. Okay, f of x equals x squared minus x minus 6. All right. Over here is the graph of that function. All right, if you were to go graph it. Now they highlight 2 points, negative 2 comma 0 and 3 comma 0. Those 2 points are where the graph does what? What does the graph do at negative 2, 0 and 3, 0? Please, not everybody at once. I can't handle the control. No, not the behavior. At negative 2, 0, and 3, 0, the graph does what? Crosses the x-axis. Very good. Okay? Crosses the x-axis. All right? That's in function notation. Okay? Now, down here with the quadratic equation, notice how it's the exact same thing, right? X squared minus x minus 6 here, x squared minus x minus 6 here. Now, what makes an equation an equation? The equal sign. All right, and the equal sign means that the left side and the right side are the same thing, right? You've been taught that since you were probably like in 3rd grade or whatever. Okay? If it's an equation, that means the left side has to equal the right side. So this one they make equal 0. All right? Then they go figure out which 2 numbers make this equation true. Just like you've always done. Right? That's what we do when you solve an equation. You find out what x will make that equation true. It's what you do. Now you have 2 numbers that'll do it. Those 2 numbers happen to be negative 2 and 3. Have you seen negative 2 and 3 here recently? Yeah, because it's where the graph does what? Crosses the x-axis. Very good. Okay, now let's connect all these dots. Everybody ready? Here we go. F of x, function notation, is a fancy way to write what letter? Y. Okay. F of x is a fancy way to write y. And whenever you touch the x-axis, your y value is what? What's your y value when you hit the x-axis? 0. It's 0. So what they do is they miss a step. They don't show a step. From here they say f of x. They miss the part where they say y equals x squared minus x minus 6. But then instead of writing y, they write 0 down here. Everybody see that? These two the x squared minus x minus 6, f of x equals x squared minus x minus 6 are the same thing. Back up to these two now. Roots and zeros. I'm going to start with 0. A 0 is where the graph of a quadratic function crosses the x-axis. Right here and right here. You get zeros from functions. Roots are the solutions to a quadratic equation, which are these two, what makes the equation equal. But these two and these two are the same what? Same two, starts with an N. And U, numbers. They're the same numbers. Roots and zeros are the same thing. The only difference between them is what notation are you speaking of. Roots is used when you're talking about an equation. What we're going to mostly work with is zeros. Zeros are when you're working with a function. So, that was a very long story, beginning, middle, and end, climax, all the other good stuff, to say, hey, those two are the same thing. Okay? Plot twist. Alright, everybody good? So here's what we're going to do today. X squared minus 3x minus 4 equals 0. We're going to solve that by graphing. Okay? Here's why I had to go through the whole drama set of everything we just did. Because you need to know, and make it click in your head, come on drawing, there we go, that you can replace this 0 with y. But only 0. If it's any other number, you can't do it. Only 0. Okay? So y equals x squared minus 3x minus 4. Now, as you guys know, Mr. Mormon loves technology. So guess what we're going to do? Put it in there, alright? I wonder how that sounded on video. Someone go back and watch this and make sure, let me know how it sounds. That part. Probably sounds dumb. X squared minus 3x. What was it, minus 4, right? Minus 4. X squared minus 3x minus 4. Okay. And we hit graph. Pretty. Okay. Pretty good. Now, what we're going to do for this, we're going to go to your table. And we're looking for the solutions. Remember what we're doing. We are looking for the solutions of that equation, which means we are looking for where that graph crosses the x-axis, which means our y value is going to be what? No. 0. Your y value is going to be 0. Now, here's the catch. What's up?
Is it the 4, 0?
And?
And, 0, negative 4.
No, you want your y value to be 0. Negative 1, 0. Okay? That's just what I was about to say. Here's the catch. You might have 2. Okay? That's where quadratics change. You go from one possible answer to 2 possible answers in most cases. There's 2 spots. If you look at the graph, it crosses the x-axis 2 places, right? Here and here. So when you go to your table and you look for y equals 0, you need to be looking for 2 y's that are equal to 0. Right, there's one. So its corresponding x is one of your answers. So one of your answers is negative 1. And then you keep on looking. And there's your other one. Your other y value of 0. And its corresponding x is 4. Whoops, wrong button. So your two answers to this are -1 and 4. And just write. Now, here's the catch though. Do not write these as an ordered pair. Okay? You write them, you can write them. Here's the catch, okay? -1 and 4, not an ordered pair. -1 comma 4, technically not an ordered pair. Whoops. That's an ordered pair. That's not good, because then you're saying that this right here is your solution, and it's not. Okay? So I don't care how you write it. You can write it x equals -1, x equals 4. You can write it or -1 and 4. You can even do -1 comma 4. I don't care. But you cannot make this in parentheses. The second you do, it becomes an ordered pair. I think I'm reading that as you think it is an ordered pair, and it's not. Because they're two separate points. Okay? Now, if you want to write it as like come on. Oh, I'm on the eraser yet. -1 comma 0 and 4 comma 0, that's okay. Because that's the actual points that they are. Okay? But you cannot put the two solutions into an ordered pair together. Okay? Mr. Taylor.
Will you sometimes just one?
Yes. That's what we're doing next. Okay? Easy enough? Fantastic. Next slide. Here's what we're getting to. All right? And this is going to be important come next week. Next week, Tuesday, I guess it would be. This is the graph. These are the three different kinds of graphs you can have when you have quadratics, at least as far as they're touching the x-axis goes. Sometimes you can have two real solutions. That's where it touches it twice. That's your most common. Okay, most common, right there. Occasionally, you'll have it when it touches it one time. Okay, I told the other classes that that's your second most. Honestly, it's probably your third most common of the three. Okay, that doesn't happen all that often. And the other one is when it doesn't touch it at all. That's when it has no real solutions. Okay, no real solutions. So these are the three possible outcomes. So whenever you go to your calculator and you hit graph, first thing you need to do is, whenever you're trying to find the zeros, is look at the graph, see how many times it does touch the x-axis. Okay? If it touches it twice, you're looking for 2 zeros in your y column. If it touches it once, you're looking for 1. If it doesn't touch it at all, you write no real solutions and you're done. Okay? Make sense? Fantastic. Next one. Ah! What the heck? 14 minus x squared equals -6x plus 23. Holy Jesus. Yeah, boy. Is that in standard form yet? Does that equal 0? Does it need to? Mm-hmm. Can you make it so? Yeah. Do some algebra things. Okay. So we're going to add 6x to both sides. Gives us -x squared plus 6x plus 14 equals 23. And remember, these need to equal 0. I'm going to subtract 23 from both sides. -x squared plus 6x minus 9 equals 0. Okay, everybody cool with how I did that? Okay, now here's the thing. I'm going to show you guys this real quick. Would there have been anything wrong if I added x squared over here and subtracted 14 over here? There's not, okay? Now, here's the trick though. Your signs would be different. All of them. Okay, if you went to the other side and made it 0 equals, you would have positive x squared minus 6x plus 9. So yours would be different, but that doesn't matter because you know what would stay the same? Where that they? That's exactly it. The x-axis would stay the same, okay? Yes, you would have different points of your graph, obviously. But where they cross the x-axis would stay the same. So as long as you put them on one side or the other, it doesn't matter which side you do. Okay? Let's see, hit exit here. Let's go y equals. Let's clear that out. Negative x squared plus 6x minus 9. Everybody good? We hit graph. Look at that. Okay. So see how it only touches it in one place? So now you're looking for just 1, 0 in your y column. So second table. Whoop, there it is. So the answer here is 3. 3, my lord. 3. Which one we had? Negative x squared plus 6x minus 9, right? Change that 9. Change 9 to a 7. Okay, change 9 to a 7. Same question though. Okay, same question. Solve it. Change 9 to a 7, hit graph. Okay. Everybody got that? How many times does it cross the x-axis? Twice. So we're looking for 2 zeros, right? Okay, so you go to your table. Okay, and you go up and down your y's, and what do you notice? There's no 0. Okay? So what now? No, because you know it crosses twice. So it can't be no solution.
Is it like 1?
No? It's not like 1. No? We don't know for sure, at least. It might be. Okay? You can only right now you can only tell me what you do know. All right? And right now we don't know exactly where it is because it doesn't come up here, right? Everybody see that? Okay? But if we do go along our table, all right? If we look at our table, we go y values from negative 14. Follow along with me now. We go negative 14 to negative 7 to negative 2 to 1. You go from negative 2 to positive 1. Right? That's your y value. That means up and down. Okay? Now, you know if you hit the graph that this line is continuous. This graph is continuous. See that? Doesn't stop. It's not just points. Continuous. Which means every x in between these has point values, right?
So it has to be like 1.5.
It doesn't have to be 1.5. You don't know that for sure. Okay? What you do know, though, is it's between which two numbers?
Negative 21.
Do your x's. 1 and 2. 1 and 2. Okay? You know it's between 1 and 2 because at x equals 1, you're at a negative. X equals 2, you go to positive. So somewhere between being negative and being positive, you have to cross the what? You got to cross the x-axis somehow, right? Make sense? So you know, all you can say right now is that your 0 is between. There's one that's between 1 and 2. And so we know it crosses twice, so that means there's a second one, and where is it at? Between 4 and 5. because you go from positive now to back to negative. See that? You're back on the downswing. So you go from positive 1 to negative 2, so you cross the x-axis again. Okay? Right now, that's good enough. Okay? We will eventually get to the point where we know how to find these perfectly accurate, but not yet. Okay? So right now, if one shows up like that, and some on your homework will, all you got to do is look for the sign changes in the y's and write down between 1 and 2, between 4 and 5, between whatever it is, whatever x values it is, that your y's change signs. Okay, makes sense? Everybody good. Fantastic. We're going to do one more. Okay? Because I know for a fact, you probably saw one like this on Wednesday. Or at least you juniors did. Where are we ever going to use this, Mr. Warman? A package of supplies is tossed from a helicopter at an altitude of 200 feet. The package's height above the ground is modeled by h of t equals negative 16t squared plus 28t plus h, where h is the initial height and where t is the time in seconds after it is tossed. How long will it take the package to reach the ground? There's a lot of advantages to function notation. One of them is this. You can rewrite and use different letters to represent different problems. Remember when I said we were going to touch word problems? Here's us touching them, okay? See, I touched it. The nice part about functions is that you can change the letters. The ugly part is then you have to understand what part those letters are representing when you go to your xy axis. Okay? So, here's my question. Here's your quadratic, right? Negative 16t squared plus 28t plus h. What variable are you used to seeing being squared? X. Okay? So here's what I would do. I would put a little note. X here, and it's being represented in this part by t. And in this case, in almost every single case, t is representing what? T means time. Okay. In this case, time after it's tossed, right? But right there, where t is the time. Okay. H of t, you're used to seeing as f of x, right? And f of x, you think of as y, right? So then y, you're used to seeing as h, and h is probably the height. That way you know. Okay, so now you know your x is represent on your axis. Your x is representing time. Your y is representing height. Okay, here's the quadratic equation, right? Now there's one thing in here that we haven't figured out yet. It's got h of t equals negative 16t squared plus 28t plus this h, and it says where h is the initial height. So what's the initial height of the package? 200 feet. Why? Because that's where it's dropped from, because that's where the helicopter is, right? It says up there the package is at an altitude of 200 feet. So the function we're actually going to work with, negative 16t squared plus 28t plus 200. After that, you put it in your calculator. Okay? Alright, so I'm going to get rid of all that. And we're going back here. So we got negative 16. Now, remember the part that I said, you know, you have to use your x's. Okay, So you can't put t's in here, so you have to replace t with x, but it's the same thing, okay? So negative 16x squared plus 28x plus 200. All right, negative 16t squared plus 28x plus 200. And we graph. Whoop, whoop. Okay. What's the question asking? Did anybody write it down? How long will it take the package to reach the ground? So we are looking for what? If it's saying how long, we're looking for time. And time is represented by what variable here? T, but when we look at it on a graph, it is our x. So basically, we are looking for where the graph does what? Cross the x-axis. Same thing we've been doing. Okay? Because in this case, the x-axis is almost representing what? But it's a real life now. That x-axis is representing the ground. The x-axis itself, right? Not x values, the x-axis itself, representing the ground. The y-axis is acting like how, put it in real life, the height. How high up the helicopter is. Okay? So the helicopter's up at 200 feet, right? It tells us that. So that means if we zoomed out all the way up to 200, that's where my cute little helicopter would be. I'm not going to draw a helicopter, I suck at drawing. Okay? The line represents the package basically in its free fall, right? So at 1 second, which is right there, it's that high, wherever it is. 2 seconds, it's up there. 3 seconds, up there. 4 seconds, okay, we're getting closer now. So to the best of your abilities, how long does it take the package to reach the ground? Between 4 and 5 seconds. 1, 2, 3. Here's 4. Here's 5. That's where it touches the ground at. Okay? Same logic if you went to your table, right? It's positive. It's positive. It's positive. It's positive. It's positive. It's positive. Negative. So at exactly 4 seconds, you are 56 feet off the ground. At exactly 5 seconds, you're negative 60 feet off the ground. Which isn't a thing, right? So somewhere between 4 and 5 seconds, that package lands. Make sense? Okay. So see, at 0 seconds, you're at 200 feet. See how that works? 1 second, 212. Which I guess they throw it up. I don't know what that. I don't know. Anyways. Okay. One last question. And we're done for the day. What about over here? What about this one?
-2 and -3.
-2 and -3? Between -2 and -3? Okay. Booker, let me ask you this question then. Have you ever, do you come from like Back to the Future movies? You know what those are?
Yeah.
You seen that?
Not Terminator.
Like the time travel and stuff, right? Yeah. Is that what you're doing right there? Like going back in time? Oh yeah. That's cool, man. Let me know. Let me know if that works out. Okay. Why do I not care about over here? Because x is negative. And can you have negative time? No. Time's not negative, right? It's real life. It's a real life problem, real world problem. So you only care about the positive stuff over here. Okay? You don't care about negative 5 seconds ago. All right. Make sense? Pretty good, pretty easy. Most of the calculator, yeah. Wrong button. Okay, homework, page 167, 1 through 13. Due on Tuesday. All right, due on Tuesday.